Go, and you're recording, I assume. And I'm going to click the OK there. Okay, so thanks, and this is the overview of the talk. I'm not quite sure what it is now, so I'm looking at this. This is the overview of the talk, and I'm going to start with an introduction on and focus on bubble future. So the initial part of the talk is about the bubbles as a topology, one of the two main topologies that I'm going to talk about. And then I'm going to move on to rings, at least the rings work that we're doing. There's lots of work on rings going on and bubbles going on around the world, as we'll hear more about. And towards the end of the talk, and I hope there is sufficient time, I'll talk about what these PhD students have been doing. But the first part is a sort of review part of the talk. Okay, so just to sort of jump to the summary in a way, there are an awful lot of interesting shapes and topologies that you can make by using radio frequency dressing, and I'll explain how radio frequency dressing works in a minute, especially for the benefit of the students. For example, you can make these shell potentials, you can make rings, you can make double rings in principle. This is just theory at the moment. You can make double shells. This is experimental results. There's an all RF and microwave made proposal for a lattice, and you can make toroidal surfaces as well as ring potentials. And I'll mention a few more of those in details, but not all of them. There isn't enough time. We reviewed a lot of all of this back in 2016 and 2017. Papers that are easily available, if not open access, then on the archive, and that's a good place to go and find out more about it. Okay, so why matter wave bubbles? I'm starting with the bubbles part of the talk. What's interesting about them? Well, there's a whole list of things here. So, for example, it's a different topology for matter wave interference. You can think about what happens if you collapse the bubbles. You know, if you release the trap that's holding them in place. And by the way, some people will call bubble potentials shell potentials. They're essentially a similar kind of thing. You can think about stirring them up, and if you stir them, then you make vortices, and there are rules about how many vortices you can have on a bubble potential. So there are limitations. They need to come into pairs for reasons that become clear when you look at all the vortex lines, for example. So these make topological questions for the bubble shape. Vortex dynamics on curved surfaces is of interest. If you have a bubble shape and the curvature varies around the bubble, then how do vortices move around on those shapes? That's already understudied by Vetter, for example. The condensation temperature on a bubble surface is going to be different from normal condensation temperature. So the topology changes the condensation temperature. This was an interesting result that came out already in 2019. People are interested in tunneling between multiple bubble surfaces, concentric bubbles, for example. You can think of it as perhaps a probe of microgravity making ring traps, as I already mentioned, and even making models of other systems. For example, a model of the expanding universe, which is the image on the bottom left over here, although it's done in low dimensionality there. Or in the far future, you could think of something like, for example, modeling the atmosphere of Jupiter using these kinds of sort of spherical systems. Who knows? So looking to the future a bit, people are thinking now, after the bubbles were made on the International Space Station, which gathered a lot more attention to the subject, people are thinking a little bit about drop towers, for example, in Hanover, and other drop tower type experiments around the world, and other ways of making the bubble, which don't involve going to space. So, for example, the BEC mixture approach doesn't use radio frequency dressing, but in this talk, I'll just focus on the radio frequency dressing approach. Now, a lot of these points that I've just made was summarized in this paper, which came out last year, which was a sort of forward look on where things might go on quantum bubbles in microgravity. So thinking more about the sort of work that goes on in the International Space Station. I'm very pleased to see that several of the authors are here. So Nathan is here at the conference. So is Nasser and myself, and maybe one other as well. So it's good to see us here. And there in that paper, we were all as a group trying to look forward to what may happen in the next 10 years, let's say, in these kinds of experiments. So as well, another sign of activity in this area is this special issue, which originally had a deadline of March, but I gather it's been extended now. I'm not quite sure where, maybe end of the year or something. And did you say end of the year? Anyway, it's got an extension. Hopefully a long extension, because I've still got to submit my papers to that. But anyway, active area of work. Right. So now it starts at the beginning. I generally like to explain for people who haven't encountered this before, though I know, looking at faces in the audience, several people here have heard me talking about this before. But for people who haven't heard this talk, how is it this bubble idea works? How do you make these bubbles? Well, consider, at least in a one-dimensional picture, this arrangement for radio frequency evaporation. So students who have done some cold atom courses are maybe familiar with the idea of using RF for evaporative cooling. And here you have some atoms. Here you have an F equals 1 set of rather ideal potentials and a radio frequency resonance over which hot atoms will escape. If you make this radio frequency very strong, so it has a strong coupling, then the relevant potentials that the atoms will be moving on are these adiabatic potentials. And you realize that when you have this strong coupling situation and you diagonalize the potentials, you get these avoided crossings here. And we've now turned this evaporation system into a double well potential in 1D. And if you're able to do that in all 3 dimensions, then you can go to this kind of shell potential where one of the wells, the double well, is here, and it has an opposite well on this side and the same in every direction. And this is an example which is shown for applying radio frequency to the Yoffie-Pritchard magnetic trap, for example. Now, I often talk about radio frequency dressing. The dressing language really, for me, has its origin in Claude Cohen-Tanuji's work. His work, of course, was in the optical regime. Here we're discussing things that happen in the microwave and a little bit in the radio frequency and a little bit in the microwave regime. And that means that we do not have the spontaneous emission that's present in the original idea of optical dressing that Claude Cohen-Tanuji proposed. So we don't have that loss process going on. But nevertheless, it's useful language. This is my second way of explaining how it is that you can make these bubble states, for example. This is supposed to represent something like you would see for a Zeeman splitting, but the coordinate here is space and not magnetic field. But if you have a linear field gradient, approximately a linear gradient, then this is how the energy levels will look. Here's the radio frequency resonance in the upper picture. And it means that if an atom is sitting on this potential, it feels the downward or the expelling force on the downward potential approaches the resonance, and provided it doesn't go too quickly through the resonance, it'll adiabatically get transported to this potential, where eventually it decelerates, turns around and goes back. And the overall effect is a trapping one where it's oscillating backwards and forwards from this part of the upwards potential to this part of the lower potential, or in other words, exactly like that. So that's another useful picture for how these things work, although the potentials are not necessarily linear or potentially perfectly harmonic or whatever. Okay. The key, in a way, mathematically, in a kind of semi-classical approximation for the dynamics of the atom in this radio frequency field as it traverses it, is the Landau-Zenner model. Landau-Zenner model, originally for 2-level atoms, describes nicely how the atom divides itself when it enters this crossing. So that crossing is a bit like going through here, and then you encounter this interaction, and if it's strong, you stay on the adiabatic pathway, which is the upper red curve here. Now, I noticed that the talk after me is about Landau-Zenner as well, or mentions it, so I won't say too much about Landau-Zenner, except that it says that in the adiabatic limit, your transfer, which is adiabatic, happens very, very quickly because of this exponential in the transfer of atoms to the adiabatic state, which depends on the square of the coupling constant. Okay, now to experimental realization. Actually, the first realization of trapping in these shell states was not in space, but in Paris and on the ground. This was Blaine Clarin's group, and showing their early results at 2 different radio frequencies. And here you see the interesting feature that if you increase the radio frequency, the radial distance of the shell increases, and that's because you're feeling the resonance as you go outwards in the magnetic field. You move the magnetic resonance, you make the bubble bigger, and this starts to show how these things are quite sort of flexible and adaptable. Jumping to quite a few years now, this has been taken to another sort of level of achievement by Chris Foote in Oxford, who's made sort of double shells, and he's interested in tunneling experiments between these two shells, and he's achieved that, which was not such a simple thing in the end. The way to look at his double shells is to use this picture in a way. It's one way of doing it anyway. So this is the picture of the single resonance making a bubble. To make his double well here, so here's one well, here's another well simplified, he needs 3 resonances to do that, not 2. And you can see that it's 3 resonances by following the path of the atoms. If they would have too much energy, it would go like this. Obviously, you want them to sit in these potential wells, but you can see if you go up, and down and up, you have one well around here, the other one here, and this is an unstable point. Okay, so now we go into space, and it's nice having Nathan Lundblad in the audience here, because he gave me this slide some years ago, and this is showing where the Cold Atom Laboratory is, which is where the bubble experiments were done, along with a few other experiments in the International Space Station, right next to the exercise machine, which I guess means that you can't operate the experiment when the astronauts are exercising and doing other things, but it's done at night, I gather. These were the results that were published in 2022. On the left here, we're seeing the bubbles on the International Space Station. On the right, we're seeing one of the experiments that I very much wanted to see happen years ago, which is the dynamics of release from the trap. What happens? In a way, I had been imagining a long time ago that, we can maybe do some kind of Boson-Nova type thing where this sort of spherical shell collapses in on itself, and I thought the collisions between the atoms at the center would be very interesting. Here, though, we don't have a spherical bubble at this point in time, and the dynamics is very complicated, and furthermore, the initial states of the system are not looking exactly like uniform bubbles. What are the reasons for that? Why doesn't this look like a nice shell? Well, a nice shell state. Well, there are multiple reasons. Some things are due to imaging direction and the way the imaging is done, because it's measuring the column density of the atoms, and it's at unusual angles and so on. But another aspect is to do with the fact that fundamentally these are fields coming from an atom chip. So the experiment is an atom chip, actually one of Dana Anderson's who left earlier. And the atom chip is an asymmetric way of making trapped atoms underneath it when you're on the Earth. And because it's asymmetric like that, it means that fields, for example, from coils near the chip to make radio frequency fields and so on, they are stronger near the chip and weaker further away. Usually you don't care about those details too much, especially if you're trapping the atoms at a point. The problem here is that we're making an extended object, a large object, relatively speaking, where bits of the same object are some are closer to the chip and some are further away from the chip. And that means you have to be careful about how you arrange the local magnetic fields that are local to the bubble. And that causes, in a complicated way, some of the asymmetries. And I have a few more comments to make about that. Some time ago, we did make a model of the chip that was in the International Space Station to have a look at these asymmetries. And indeed, we found similar kinds of results. This is using Gross-Pedievsky equation. And we see that we get partial bubbles for a few atoms. I mean, you can improve it by putting lots more atoms in here. And you can get a ring, but you can see the atoms want to go to one side in this case. So don't go into the details of that here. We did come up with a scheme, as I was thinking earlier today. We did come up with a scheme to compensate the asymmetry by using 2 types of field, one radio frequency and one microwave, and using the asymmetries in the field from the coils of both to try and cancel each other out. And that can be quite successful, actually, as we see in this bottom left picture, which is using microwaves. Anyway, some concluding points on how the bubbles are made and making your own sort of schemes for these things. So things to care about are the surface variation in the Rabi frequency. because this surface variation in the coupling strength can affect where the atoms want to go, and it can mean they sort of get sucked to one part of the shell. So this is something that has to be kept into mind. If you have a lot of atoms and repulsive interactions between them, that can help, but you still need to be careful about that. Also, zeros of the radio frequency coupling must be totally avoided. Not easy if you use something like a quadrupole trap, but straightforward in a way if you're using underneath a Yoffie-Pritchard type trap, for example. And just recently, it's been pointed out that surface variation in the trapping frequency can also have an effect. So by trapping frequency, I mean within the skin of the bubble, the vibrational frequency, which is perpendicular to the surface. And if this is going high in one place and low in another, then you have a spatial variation of the energy of the ground state of that harmonic oscillator, and that actually causes atoms to move to one spot and away from other areas. One thing that's not an issue, as it says at the bottom here, is the lifetime. Long lifetimes of 30, even maybe 60 seconds, at least on Earth, have been made. Now, I get asked some frequently asked questions, so I answer those now. The nonlinear Zeeman effect is not a problem. So there's already a paper about that showing that even though the nonlinear Zeeman effect causes the resonances to be smoothed out, they sort of separate and go into different areas. This doesn't cause much trouble except for a change in the frequency of that transverse frequency of the trap. Another question is, can we cool a radio frequency made trap like these bubble things with radio frequency? Can we do evaporative cooling within the radio frequency trap? The answer is yes, it's been demonstrated. The only thing that gets in the way of that is the fact that if you're dealing with shell states or other two-dimensional like things, then the evaporative cooling is less efficient than it would normally be with a blob. But some experimentalists are quite optimistic about that. And I repeat, lifetime of these things is not really a practical issue. Right, so closing on bubbles, I just switch now to the ring topology and say a few words about that. So early successful rings on a large scale, Nobel Phillips had a small ring which precedes all this, but early large scale rings were based on this idea of taking a bubble and using the bubble, e.g. by intersecting it with blue detuned light sheets of some kind. So we originally proposed a whole standing wave of blue detuned light, and then you trap you trap the bubble potential and the atoms within that. This was realized by Chris Foote in his images you see on the right here, and later also done by the same Paris group. Other ways of doing the rings, there was a proposal by Jörg Schmidtmeyer's group for a sort of vertical ring like a tire here, but actually it's more like a tin can. I think it's a very long sort of cylinder potential, and that also is of interest by people who are interested in topological things. And then we come to the toroidal surface that I mentioned. This was proposed by Fernholz in Nottingham and his colleagues, and involves quite complicated, well, complicated in one way and not in others, sort of double permanent magnets here and coils that make a rotating circular polarization as you go around here, and that combined system can make a toroidal trapping surface and also double ring systems. And from earlier this year, this is his imaging of atoms in his toroidal trap, which he's done successfully so far. But in a sense, for me, the highlight of control and making fantastic rings is local to Crete, and that's Wolf von Klitzing's approach, which is to take the bubble potential and not add optical pieces to it, but just shake it. So he shakes it up and down. Maybe he talked about it in the summer school. No, he didn't. Yes, he did. A bit. Okay, so he shakes it up and down, and then the time average potential for atoms moving slowly in this shaken up and down bubble turns out to be a ring potential. And this makes him have a lot of all electronic control of what these ring potentials do. He can tilt them, he can rotate the tilt and all sorts of things like that. And he can make very, very big rings, so 2 millimeter scale rings here with ultra cold atoms in them. So those kinds of things make it interesting to ask questions about, what's the expansion of these rings really like? Now we get into the bit about some of our work. And I was interested in taking a unique and different approach to what some other people are doing. And the approach that I'd show on the next slide was motivated by this work in quantum optics, nothing to do with matter waves, but I'm going to apply it to matter waves. So this work in quantum optics involved a phase space way of making a number state by taking a superposition of coherent states, also known as Gaussian states, around a ring. So that we take actually a continuous integral of coherent states around a ring in phase space. And when you do that, you make a number state. So I thought, well, for our ring states, why not take a ring of Gaussian states around a circle and see if that matches the situation for the ground state of a ring potential. So now here I have X and Y as the axes. So these are not X and P as they would be for phase space. It's X and Y. And I distribute a whole load of Gaussian states around on a ring. Now, why is that interesting? It's interesting because we know analytically, we forget the interactions for now, we know analytically exactly how a 3D Gaussian blob will expand if we're doing expansion. The idea of the expansion here is to have diagnosis of what kind of ring system you've got in your vacuum chamber. So you can analytically calculate this sum around here, and you can get analytic results for the probability density and everything. So we have formulae that explain also for the shell states. And we know exactly then how it's expanding in time, and we have a prediction then for the number of fringes, roughly, that you will see at any particular time, because that changes. The real dynamics look something like this. So what we see is cross-section through a ring on the left and through a bubble or shell, because we were also interested in the expansion of shells on the right. And what you see is how they spread, overlap in the middle here, and create fringes. And all this is analytically calculated now in a paper which is in preparation. This full draft should get submitted soon. So that was an ad hoc approach. The question is, well, how good is that? So we can take a ring, an actual ring potential in 3D and put a condensate, do the Gross-Podolsky equation, find the ground state, and integrate the expansion of that thing. So we can do all that work the hard way with 3D Gross-Podolsky or 2D Gross-Podolsky equation, and then compare it, the fidelity, with the approach that I've just taken. Sorry, this approach is now without interactions here, with interactions on the next slide. So without interactions, the fidelities are many nines. We have 4 nines up here and going higher. So extremely high fidelities for both the ring situation using this coverage with coherent states, or if you prefer Gaussian states actually, both for the ring and the shell potential. Introduce interactions and that degrades a bit. So here we've introduced different numbers of interactions. We look at 1 minus fidelity, so infidelity here as a function of time. And we see that if we have small numbers of atoms, then this is, for example, the lowest black curve here is at 10 to the 3 atoms, then it's perhaps a tolerable infidelity, but it gets worse and worse as the interactions increases. So for some small numbers of atoms, it's actually quite good. You can see what's going on here, that basically interactions, the repulsive interactions actually disturb this approximation of the Gaussian functions that we're using. We're playing around with some other things, including tilting the ring and doing a long time expansion. And a typical feature that's quite intriguing about these is that you get these sort of sharp notches in the expansion, but that's a work in progress, and I will not say much more about that. Right, so finally then, why are we interested in rings and things? Well, there's lots of reasons. I think I got a bit more interested in the rings because of trying to make a compact rotation sensor, which is made by having a sort of, in this case, microwave produced ring trap. which is enclosed, and everything done in that case by microwave induction and RF fields coming in from outside and so on. But at some point, if you're going to think of making a rotation sensor that way, you have to think about, well, what is going to be the dynamics of the matter waves that I have inside this circular guide? How do matter waves in circular guides actually behave if I don't have, a continuous long stream, but if I send a pulse? So, for example, you're seeing here in the middle a Gaussian wave packet, which is carefully aligned, being projected around the ring, and you're seeing how it moves. And you might notice, maybe not at the back, but you might notice that as it goes around, it starts tilting with respect to the tangent of the arc. There's a bit of a sort of tilt there. Well, we've now understood how that happens, at least mathematically. We have all the equations that describe it by using an approximation based on Gaussians. And it's quite complicated. It ends up as a set of nonlinear coupled differential equations. And basically, we have found that all the necessary transformations, displacement, rotation, and squeezing that enable us to go from a Gaussian somewhere else and recreate an approximation to the Gaussian that's going around this ring trap. So that's done, but needs further work to find the corrections. So to conclude then, and I'm slightly surprised I'm not over time. To conclude, we have the basic results of many different types of topologies being created for atoms, and they are going on to many different applications, I would say, in the future. And finally, I just thank all of my collaborators who I put there, and thank you for listening. Thank you.
Thank you very much. Yes, and then Eric.
Thank you. Found interesting your more or less representation as a lot of Gaussians. So normally when you have these in a one big guide, and you get this more or less space fluctuations, space is breaking. So now how is this then? I think it's originally similar. So is it then somehow...
I should clarify. So this picture here is not it's not something that involves, for example, Gross-Berdievsky or interactions between atoms. So this is without interacting atoms at first, and then we end up with these excellent fidelities with no interactions, and therefore I think no phase fluctuations developing all around. And then we've tested it with Gross-Berdievsky and seems good, but it was an ideal case of Gross-Berdievsky ground state and so on. We didn't sort of put any noise in or something like that.
Thank you.
Yeah. But an interesting idea, actually. I mean, maybe the noise could be added to the different Gaussians somehow. I've got a thought now from that. Thank you.
Just a technical question on your last slide, because you had the sort of, yes, this sort of split step versus Heather method. Are you saying that one of them is sort of the incorrect and one is the correct way of calculating the dynamics, or I guess I just didn't quite understand what was going on here.
The main point here is that we developed the mathematical tools to understand the essential behavior of the wave packet motion pretty much exactly. So we know what the tilt is that you see in the previous slide, that going around there, it's sort of skidding around. So we know all that detail. That's been developed into a set of transformations that would take us from a Gaussian, which has got equal widths in X and Y, to exactly this state here on the right. Now that's good enough in a sense, because we know the precise angle from the tangent that comes from that analysis. Doesn't give us some of the fine details. So split step here means that we did a numerical calculation, and that was a split step numerical calculation. You see that there is this curvature. That would be either another transformation, and I don't know what it is, and I spent some time thinking about it, Or what we will do is a trick that I've done in the past, which I go to this local basis through all these transformations, and in the local basis, you're mainly in the ground state of a 3D or 2D harmonic oscillator, but then you do time-dependent perturbation theory to see, what are the corrections from the first state, second, third, and so on, working in that basis. So the purpose of these transformations was to take us to that local basis, but at the same time, we understand, because we know what our rotation angles are and everything, we understand how to describe this shape. This shape is really the ground state of a local basis that we found through these transformations that would give you the core of this actual numerical result, and to which we can do perturbation theory effectively later.
Can you go back to this special issues?
No, of course.
Yes, so thanks a lot for showing this slide about the special issue that we are guest editing with Nathan together. This is still open. The date is end of September. If you want to just join with the paper there, it's called quantum bubbles, but we are taking also any other curve topologies. Just wanted to advertise about this, and thank you very much for showing this, and thanks a lot for your talk.
Thank you very much.
You missed something? Yeah, it's there.